station. So something wanted station. So something wanted messages to a device pretty fast. This wasn't a big limitation. Also, the process will respawn fast as well. So now I had the ability to write anywhere I wanted after the heap. And then I looked at, what do these function pointers actually do? And what was kind of convenient is that it turned out that there was the function pointer that was pulled out of this buffer, but nearby, all the parameters were also pulled out of the buffer. So this was pretty good. I could partially overwrite the function pointer and make calls to kind of what I wanted to, also with the parameters too. So awesome. Except, so as I wrote this exploit, I was talking to Jan Horn about it, and every time he would be like, "But Natalie, how are you going to bypass SE Linux?" And I was like, I have plans. I'm going to write a file, I'm going to DL open it, I'm going to map a page, read, write, execute. I tried both of these. They are both blocked by SE Linux. So, I got to message Jan and be like, "Hey, you won't believe what just happened." And I got Seth and Jan on a video call, and I was surprised. They actually made pretty short work of this. So the plan they came up with was, so to start off, write the shellcode into memory. Seth's going to talk a bit about this later, but due to the memory in the decoder, there's a 32K limit, and that's just because that is the largest amount of memory I can control in a frame of the DD plus format, but that's still quite a bit. So the plan was to get this into memory, then call fopen on proc/self/mem, ideally a lot of different times, so I can just sort of guess the descriptor it gives back, and then use that as an absolute value. Then call pewrite to write the shellcode to stack check fail, and then call stack check fail. And the reason I picked stack check fail is just because that's a low contention function. It can be overridden, and it doesn't matter because it's only ever called if you sort of have problems in the first place. So this mostly worked, except I had to figure out how to call pewrite. And unfortunately, this wasn't available. This binary decoder never calls pewrite, it never calls fwrite, it never called anything I could use for that functionality. And it also kind of had limited ROP gadgets. Because I was, overwriting the function pointer using the same trick where you overwrite 2 bytes, I only had ROP gadgets that were, between 26 and 26 FFFF, only a small range of them. So I ended up looking for gadgets, and I found this gadget. I call it the best gadget ever because it actually worked, but it is the worst gadget ever. All it does is it takes something out of X1, it adds 157 in hex, and then it puts it back into the address at X1. So, if that's all I got, here was my plan. I called memcopy and basically copied a pointer to libc out of the GOT table, and then used memcopy to copy the real pointer into heap memory. Then I called this gadget, as many times as were necessary to increment this pointer by 157 until it was almost at pewrite. Then I overwrit the last byte of it so that it was exactly at pewrite, and then I was able to call it. So that was exciting. This led to arbitrary code. So next up, Seth is going to talk about how we got from the media codec execution to kernel.
Sweet, thank you, Natalie. Is this working? Yeah, we good? Great. So now what? Now we have shellcode execution and media codec, and we need to figure out how to get that into something better than shellcode execution and media codec, ideally into root. That's where I come in. I love getting root. That's my whole job. So buckle up. We're going to start by looking at the media codec SE Linux context. This is the context we've popped into in user land. This context is what's used by the Dolby decoder to decode data, and it's intended to be constrained. We'll talk a little bit about what constrained means. It's basically sandboxed. Someone in a moment of brilliant predictive power thought, oh, hey, we have all these codecs, and maybe they might be poppable, and like maybe we should like put them somewhere that's a little bit more difficult to pop. So they are put in this like sandbox context that's ideally a little bit more difficult to hack than your typical context. And it was only separated out, maybe, I guess it was like Android 7 or something. I guess that's a fairly long time ago. And basically all of like your non-secure sort of decoders and encoders, particularly like hardware encoders and decoders, exist inside of this media codec process. This constrained process, you know, as we've noted, the risk of RCEs in these media decoders, that's pretty well established at this point. We've seen bugs like this before, like stage fright, and we had this idea, like that is known. That's why the media codec context exists. But the reality is that like that means that this context is essentially, we should be treating it as like unprivileged, dangerous. Remote things can happen in it. It needs to be carefully protected. And any bugs that can happen in that context that could get you privilege escalation, those are really bad. But the unfortunate reality is that when most people think of untrusted and unprivileged context in Android, they think of like one specific SE Linux context in particular. You can, if you know it, you can shout it out. If you said system server, that's wrong. It's not system server, it's untrusted app. And this is the context that like basically everyone thinks about if they're thinking about like, oh yeah, you want to pop something, you need to start an untrusted app, and then you can find a privilege escalation from there. And those are the only privilege escalations that matter. And that mindset exists at Google. And I know that mindset exists at Google because it exists within myself. And I also have this idea of like, oh, untrusted app is the only thing I should care about. And you know, if I design my tools, I start from untrusted app and let's figure out privilege escalations from there. But that mindset is very dangerous because there are other dangerous SE Linux contexts. Here is a non-exhaustive list of all of the dangerous Android SE Linux contexts. Obviously, we've got untrusted app. We have media codec, as we're going to talk about during this presentation. Isolated app, of course, that's the thing that Chrome runs in. There's also media extractor, which does more media parsing, platform app, which does other media parsing, and then you could also start talking about like baseband and Wi-Fi and Bluetooth contexts, which also do like important remotely accessible things. All of these things are potentially interesting to attackers. If they're coming from a remote context, they might be popping out into one of these, and we Android defense researchers need to care about all of these contexts, not just untrusted app. So my big question here, as we started to go down this Dolby decoder exploitation route, is like, well, is media codec as secure as it should be? Because I sort of suspected it was not. My suspicion was that media codec was not very well audited, and I'm particularly interested in what Linux kernel drivers might be accessible, because that's, if you've ever watched any of my other presentations or read any of my blog posts, you've probably figured out by now that seems to be the only thing I care about right now. And it seemed likely to me that there's some media decoding kernel driver in media codec, because that sort of seems like what media codec would be for. So let's find out. I have this little tool that I wrote called Driver Cartographer. It just looks for drivers on a device coming from various different SE Linux contexts. It can analyze the device sort of automatically. And it found this interesting device sitting on the Pixel 9 called Dev Bigwave. Huh, that's interesting. What is Dev Bigwave? You can see media codec can access it, it can ioctl it, it can open it, it can do all the things you need to do to attack this driver. Turns out it's custom Google-made silicon. It's like for AV1 video decoding in particular. And you can read about it at this link, which, take a picture if you want, because it's about to go away. So let's take a look at the main ioctl of this Bigwave driver. It did not take very long to find a bug. I mean like 2 hours or so. And that happened in like the same week that we were also looking at the Dolby decoder, so fun detail. So here's that code here. You can see there's a bunch of different ioctls. The one we're really going to care about is just this big O IOCX process one. You can see that I want to point out that like there's this inst here that's associated with the file's private data, right? And if you do kernel hacking, you know that means that if the file goes away, very much likely this instance is going to go away, and that's the case here as well. If the file gets closed and the file disappears and the file gets freed, that instance is going to go away as well. That is going to be important. We also have this moment where the register values are copied from userland. Those are the register values that are going to be put in the AV1 video decoder silicon later. We then place that instance onto this queue, a priority queue, where it's going to get picked up. We're going to see from who by who later. And then we enter this wait for completion timeout. This is just going to wait for 16 seconds and just hang around hoping that at some point whoever's picked up this job will complete that work and return it back to me. If that job failed to complete, and we'll talk, basically the job is just something inside of the instance, and that's sort of just, if I refer to the instance and the job, they're basically sort of, they have exactly the same lifetime. If the job fails to complete, then the job is cleared from the priority queue on that line, assuming that the job is still on the priority queue, which it might not be. And at the end of that, we return, and whatever ref count we had saved because we're in an ioctl gets dropped. That means if the FD is closed, thank you. If the FD is closed, instance goes away. I love technology. I promise. This is big O worker thread. This is the thing that picks up the jobs on the other side. And we can see that it also has a wait event timeout, this time with a DQ priority queue. So this time it's picking up jobs from the priority queue and processing them. What does processing them look like? Well, it runs this function called big O run job, which runs the job on the core. What does that function do? I have it here for you. It basically, it doesn't do a heck of a lot of cool stuff. It's mostly just like hardware spin up and spin down, but you can see it pushes the registers onto the core, and then it enters its own wait for completion timeout after enabling the core, waiting for the big O hardware to finish decoding the job. And then, yeah, that's sort of a problem because, as we talked about earlier, the job could get freed if it wasn't on the if the priority queue if the job got stolen off the priority queue by this worker thread, and then at the same time the other original ioctl caller ends because its 16 seconds have elapsed, then that thing can return. The ref count on the struct file is dropped. The job can be freed, the instance can go away, but this function here, big O run job, which exists in a separate worker thread, can still be referencing the job at the same time. The trick is that we just have to get this thing to run for 16 seconds. And if that happens, the user after free only happens after big O unlocked ioctl exits, and only if the worker thread is processing the job at the same time that big O unlocked ioctl exits. Which means I need to queue the job inside the unlocked ioctl, and then I need to wait 16 seconds, and then I need to have the job be in use by the worker thread right before clear job from priority queue tries to dequeue it. And that means that it has to be dequeued and in use on the worker thread. Okay, so how do I win this race? I need to send a job to the worker thread, wait 16 seconds, and have the job in processing right as the ioctl exits. But a job cannot last longer than 1 second. As you can see from this wait for completion timeout and big O run job, there's this quick check basically that timeout is only 1 second. So a job only lasts 1 second. How do I make a job last 16 seconds instead? And the answer is I don't. What I do instead, because this big O worker thread just processes jobs in order from like when it was submitted, right? So if I queue 15 other jobs immediately before queuing this job, I can guarantee that the entire sort of process will wait 16 seconds, and then it will be processing the specific job I'm targeting right at the same time it will be processing that at the same time that ioctl will return. And as soon as the octl returns, I close the FD and I destroy the instant job, and you get use after free. And that use after free does a couple interesting things. It accesses a couple different fields that previously existed in the inst, but is now gone and could potentially be reallocated by me. We'll talk about that. There's a couple different cases where it accesses use after free. I've notated 4 of them here. But there's one in particular that's interesting, big O pull regs. You can see that accesses the job. The job has been used after freed, and it accesses the regs pointer that exists inside of the job. And let's say I could potentially control that. That would be very powerful. And inside of big O pull regs, it's just simply a mem copy. It's a mem copy from that previous regs pointer that comes from the job, and it copies the memory from the core that is the AV1 video decoder block. The registers from that core. Where do the registers from that core come from? It comes from this big O push regs that happened earlier on in the big O run job, and that previously got populated from the unlocked dioctal. So it got populated from attacker-controlled memory. That means if I do the following sort of steps, first, I start with big O unlock dioctal, and this is your typical sort of layout with the instance and the registers, and you can see how like the job is inside of the instance, and then there's a regs pointer inside of that. And the regs pointer points to another set of memory that is actually what the regs registers are stored at. And when we first run this, when we do the copyrights from user and we push it onto the job, or we push it onto the core, we get this sort of layout where now the big wave core registers has the sort of register values previously set by the attacker. That's all by design. And then we trigger the use after free. The instance goes away while the attacker data remains on the big wave core. Then we reclaim that instance with attacker-controlled memory. It's pretty easy to do this. Big shout out to Jan. Jan is great. He had this idea of using Unix domain sockets for that reallocation. So you can just reclaim that, and basically that allows you to control all the memory. I had another way of doing that. My way sucked. His way was much better. By reallocating with Unix domain sockets, I can control that register value. And so I can control the eventual write target because I own that pointer now. And now, later, when the big O run job worker thread tries to pull the registers and move them back onto the instance that eventually should get sent back to over the ioctal, it ends up copying memory wherever I want. So this becomes an excellent arbitrary write-where gadget. But this arbitrary write-where gadget has some deep flaws. One of the big ones is that I have no idea where anything is laid out in memory because I don't know the Castro slide. I haven't leaked the Castro slide at all. And also the write is very large, 2,144 bytes, and I can't control all of it. I can control most of it, but I can't control all of it. And it's just really annoying to work with a write that big because you're clobbering over everything else in the kernel memory space as you're performing your task. So yeah, how do we get around those sorts of problems? Normally this would involve some other sort of exploit strategy. I came up with a couple that could have worked. It's just tedious. So you're trying to find like just the right sort of object to allocate over that thing to do something interesting. Actually, there's another exploit strategy that I came up with recently that would have worked really well, actually. But at the time, I wasn't smart enough to come up with that. So I ended up just trying to go down the line of like, okay, how do I defeat Castler? It turns out that it's not that hard. Especially because Castler is considered mostly dead by the Linux kernel maintainers. It's not really a first party like, yeah, we use this and now our kernel's going to be safe anymore. It's kind of this idea of like that exists and it's kind of almost just in there for legacy reasons, but we don't really consider it very secure anymore. Because unlike userland ASLR, there's some big weaknesses in kernel ASLR, mainly like hardware speculative execution. Exploitation could potentially defeat KASLR, not too difficult. I mean, I think it's kind of difficult, but suffice to say, it's not really well maintained, and so there wasn't that much effort put into keeping it secure. One of the cases where I found where it wasn't particularly secure was something called the Linux kernel linear map. This is a one-to-one mapping of physical memory and the kernel virtual memory. And it's always at the same kernel virtual address. There used to be randomization, but that randomization no longer exists. It's mainly because it's the amount of memory that technically the processor can address physically is much larger than the amount of virtual memory allocated for the linear map region. So it always just takes place at the same address. At some point, someone noticed that, and instead of saying, "Oh, hey, like we should like change that to like move it around in memory," they were like, "Yeah, we'll just remove the randomization. We just don't need it anymore because Castler doesn't do anything anyway." Well, normally this would still be a little bit more difficult to exploit because you could have randomization of the kernel physical address, well, that is the address that the actual kernel VM Linux lands in the physical memory space. Bootloader is able to do this. Qualcomm's bootloader does this, for example. If you use a Qualcomm phone, it will randomize that address. The Pixel bootloader does not do this. It just places the kernel at the same location in physical memory every time. That means that instead of breaking Castler, I can just use that address, and I'm done. It's that easy. And that was kind of terrifying, but that's great for me as an exploit writer, because now I just have like a perfect alias for like all of .data, all of kernel.data, and it's that easy. One big caveat is I can't use function pointers because that memory is only clobbering 2,144 bytes for each of those writes. I've now clobbered 4,200 bytes of memory. How exactly do I survive that? Isn't the kernel going to explode at any moment? I mostly handle this by like not caring. It turns out that the phone crashes when I turn on and off the Wi-Fi. I don't know why the phone crashes when turning on and off the Wi-Fi, and I can't be bothered to figure it out. If you want to figure it out, be my guest. Fixing my exploit is left as an exercise to the reader. You can download it from the Project Zero bug tracker if you'd like to have a go. But it's not my job to do that. I just, demonstrate cool stuff. So now I have to turn this exploit into shellcode. The Dolby exploit has space for 32,000 bytes of shellcode in random unaligned segment of RX memory. And I have a 500 kilobyte ELF file. I need to change those two so that they're much more closely aligned. First, I remove the libc requirement with those arguments to GCC. Then I implement all the syscalls. This involves asking Gemini, hey, here's my source code. Can you implement all the system calls for me? And Gemini said, yeah, sure, I'll do that. And then I took all those system calls and I plugged that header file into my binary, and it generated a bunch of compilation errors. And so I then took those compilation errors and I plugged them back into Gemini and said, fix those. And it spit out for me a new header file, and I plugged that back in, and it gave me new and exciting compilation errors. And I just kept doing that like 4 or 5 times, and eventually it started working. Awesome stuff. So yeah, LLMs wouldn't help Natalie, but I guess they decided I was not smart enough to do it on my own. So then I remove a bunch of other features that add space and complexity, and I also can remove alignment requirements with that little argument to GCC as well. And then I remove this unneeded section that helps me save some memory, and then I turn the ELF into a blob by prepending to the entire ELF just a relative jump that goes right to the beginning of the ELF entry point. And hooray, now I have an 8,000 byte shellcode blob. That's all I did. It's still an ELF, but if you just go to the entry point, it runs perfectly fine. All of the jumps are relative because it's compiled with -fpic. It's not very hard. So now I need to turn that arbitrary read-write to root. That's not very hard. I access the SELinux enforcing variable in the SELinux state struct. I turn it from 1 to 0 using my arbitrary write. I walk the task list. I find my process. Rather than creating my own sort of new cred struct to set my UID to root, I just borrow the init cred. It's in .data. You can just write that instead. Much easier. I end up incrementing the ref count of that by 1 just to make it a little bit less likely to disappear or get accidentally freed or something. And then I run the script that I have embedded in the exploit. In this case, I made the script take a picture using the device camera and send it back to a random IP address. And that's the picture, the very first picture of us successfully running this exploit. You can see that both of us are, or at least me at least, I'm haplessly looking at my screen trying to figure out why the exploit isn't working. Surprise, it was working the whole time. So thank you guys for that part. Now I'm going to hand it back to Natalie to talk about.
And yes, I was also like, why is this not working? Well, it had already started. So I wanted to end off by talking a bit about what we learned from this and how we can hopefully prevent this type of exploit in the future. To start off, I was surprised by how fast this was. The discovery time for both bugs was days. You could argue it's weeks because, we had to write tooling. We also spent time looking at stuff we didn't find bugs in, but still it was super fast. Then the Dolby exploit took about 8 person weeks, and the Big Wave exploit took about 3 person weeks for a POC, and this is where we feel like now we wish we tracked our time better, maybe 6 to 8 person weeks for an exploit. But regardless, that is not a huge amount of effort considering this is a zero-click exploit on an Android device. So after doing this, how do I think we could increase the timeline? I'm going to start off sort of with what worked well. ASLR, user space ASLR, really held me back. If you look at old exploits from 2019 on the Project Zero blog, there were lots of situations on Android where we could guess pointers. There was that part where I had to copy the pointer from the heap. 5 years ago, I wouldn't have had to have done that. Also, I discovered that sort of the low bit ASLR seemed to be like a lot more effective at stopping me than the high bit ASLR. So having the small page size with the ASLR really, it didn't make it perfect, but this made this from a perfectly reliable exploit to a 1 in 250 div. One thing I think that really would have helped here, was the zero-click attack surface reduction. I actually really like the automatic transcription feature, so, you can be so-so on like whether that should be done zero-click, but definitely there is no encoder for the Dolby Digital Plus format on any mobile device. It's a commercial media format, so I think that could have been removed from the zero-click attack surface with basically no effect on features available to users, so that's something that can prevent zero clicks for sure. Another thing that was surprising is I glossed over it while I was doing the right to proc/self/membit, but there was no setcomp policy on the media codec sandbox. And if you look at AOSP, there is one, and I don't know why it didn't make it into the pixel, but I bet if they'd tested it, it would have. So that is something that was surprising and definitely important, that it's easy to have all these ideas on how to run exploits, but if you're not testing they get in on every single device, then they're not going to be there. Finally, the patch story for this was not the best. So we reported these two bugs. There was the Dolby issue, and that took 193 days to be fixed on Pixel. Project Zero has a 90-day disclosure policy, so it was public for 84 days before it was patched. So this is like not great for a zero-click vulnerability. There was also this big wave issue, which this took 199 days to be patched, and it was public for 114 days before it was patched. And you might wonder, like, what happened here? And this was the classic diffusion of responsibility when prioritizing issues. The Dolby issue only got a bit of access, and the Big Wave issue only got a bit of access, so they were both rated as moderate, which meant they had these long fixed timelines. And Android has since changed this, and these both would be, actually one of these would be critical, and one of these would be high priority. But this is a common problem, and it led to these super long patch timelines. Just want to call out managed code here. If these things were in Rust, if they were in Java, perhaps it would be impossible to exploit them at all, and we'd have to go find new bugs if we wanted a zero-click exploit chain. Finally, I want to call out memory mitigations. One question you might be wondering is, does this CVE affect the iPhone? Because I said that frameworks had the code in it. And the answer is no, for two reasons. First, the UDC, the Dolby decoder, is in a one-click context, so there's some attack surface reduction there. But also, it was compiled with a Clang flag called fbound safety, which injects checks into structs so that it actually checks every time you access memory in a struct, is that memory in bounds. And these instructions were correct. They completely prevented this bug. So that's actually very promising, that there's this memory mitigation that could have made this bug completely unexploitable. And there's also MIE. And I think, obviously, iOS uses different drivers, but that would have prevented a driver bug similar to Seth's. So that is something, MTE, MIE, that would really prevent these types of exploit chains. So I want to end off on kind of a positive note. Obviously, there was a lot of problems that led to this zero-click exploit chain, but I think we also learned about a lot of things that could have prevented it, and I think this is something that I think we could soon really turn the corner on. There was one device where this bug was unexploitable, and these technologies are available. We have MTE, we have mitigations like fbounds check, we have attack surface reduction, we have things like Rust. So I'm really optimistic, that if device makers do everything right, we could one day in the future vastly reduce the availability of these types of exploits. It's really just a matter of investment and a matter of will. So, we have what it takes. I hope we do what it takes. Thanks so much, everyone.